everyone. I am Dr. Susmita Dey Sandhu. I'm from Bhaskaracharyya College of Applied Sciences, University of Delhi. Today, I'm going to present my paper on preparation and characterization of NBR-based composite of polythiophene and modified carbon black. So, conductive rubbers are very important for many different types of applications, but till now, whatever in market is available, they are primarily based on silicone rubber, fluoro rubber, EPDM rubber, and many other specialty rubber, along with different types of metal wires or metal nanoparticles like silver, aluminum, etc. So in this work, we have tried to develop a conducting rubber, which is low cost, at the same time is able to fulfill the requirements. So for this work, we have chosen carbon black, and we have modified the carbon black by two different ways in our lab. And along with that, we have used conducting polymer like polythiophene as the heterogeneous phase. And as a continuous phase, we have used NBR, which is a polar rubber, for preparing the sample. So the first method of preparation of carbon black is by aqua regia. So aqua regia is used in which the carbon black is dipped for 48 hours. And after this 48 hours of soaking time, we have taken it out. We have filtered, washed, and dried it in oven, and then sieved it through a mesh so that we get a fine powder. The second method of carbon black treatment is mechanochemical process, in which we have ball milled the sample for 40 minutes at 800 RPM, and then it is treated with ammonia solution and again ball milled for another 30 minutes so that the surface area is increased along with introduction of some active groups. And as I said, we have used polythiophene as the heterogeneous phase. So here we have synthesized the polythiophene in lab in using FeCl3 as the catalyst in chloroform medium for 24 hours in 200 ml chloroform, and the temperature of the synthesis was kept between 0 to 5 degrees centigrade. So the polythiophene that we prepared in the lab was characterized by FTIR, and there we can see that it has the presence of CS bond stretching, thiophene ring stretching, and trans double bond present in thiophene. So that confirms the preparation of thiophene in the sample. The two types of carbon black, modified carbon black that we have prepared in the lab were characterized again by FTIR and BET surface area. So the FTIR results show that the carbon black modified with aqua regia has developed much more active surface groups on its surface compared to the carbon black which is mechanochemically treated. On the other hand, if we look at the BET surface area, the BET surface area of the mechanochemically treated carbon black is much higher compared to the aqua regia carbon black. So finally, considering both the factors, we decided to go ahead with the rest of the work with the aqua regia treated carbon black, which has higher surface active groups. So in the next phase, we have mixed this in NBR at two different loadings, that is 10 pHR loading and 20 pHR loading. And for comparison, we have also taken untreated carbon black at 10% loading and 20% loading. We have, for comparison purpose, we have used both peroxide curing and sulfur curing. So the result shows that the aqua regia treated carbon black filled at 20% loading with sulfur crosslinker is showing the highest conductivity, both surface and volume. But on the other hand, the mechanical properties like tensile strength and abrasion resistant is better for the aqua regia filled sample at 20% level with peroxide curing, which is quite expected because in peroxide curing, since the number of bonds are only nature of bonds are only CC linkages, so that is expected to give higher strength. The elongation at break again is better in case of sulfur curing, which is again as per our expectation. So from here, we decided the overall properties are better for sulfur curing. So we, for the rest of the work, we decided to go ahead with the sulfur curing with aqua regia 20% loading. The morphology studies using ACM are compared here. Here we can see that the aqua regia treated carbon black filled at 20% level shows a uniform distribution of the fillers and a good surface finish. So in the next phase, with the aqua regia 20% filled sample in NBR with sulfur curing, in this sample, we have further added polythiophene at 2% loading, 5% loading, and 10% loading. And then we have studied various properties to see the effect of the polythiophene on its properties. So if we go one by one, looking at the electrical properties first, we can see that the surface resistivity and the volume resistivity has continuously gone down with the increase in the polythiophene loading. So that means the polythiophene is increasing the conductivity of the samples, and that is why we can see that the graph is showing continuously downward fall as far as the resistivity is concerned. Looking at the tensile strength of the samples, we can see that with increasing polythiophene loading, the tensile strength has continuously shown increase. Both the tensile strength and the elongation at break is more or less increasing. So that means the polythiophene loading is also improving the tensile strength of the sample. Abrasion resistance studies shows that abrasion resistance is good in case of 5% loading as well as 10% loading of polythiophene. We have also aged the sample at 100 degrees centigrade for 24 hours to see the effect of aging on the samples. So it shows that with increasing loading of polythiophene from 2 pHr to 10 pHr, the effect of aging is much more harsher on the samples, both the tensile strength and elongation at break. And this is quite expected because polythiophene is a conducting material, so it will also conduct the heat better than, with increasing amount of loading. We have finally studied the air permeability of the sample. So here again, we can see that with increasing loading, the permeability has reduced. So that means polythiophene is actually making the material impermeable to air. So coming to the conclusion, aqua regia modified carbon shows better surface resistivity compared to the mechanochemical modification. Aqua regia carbon black filled at 20% loading shows best mechanical, morphological, and electrical properties with NBR when cured with sulfur. Polythiophene loaded at 10% loading further improves the properties. Increasing loading of polythiophene in the sulfur cured sample from 2% to 10% improves the electrical conductivity and tensile properties in a gradual manner. Among all the polythiophene filled samples, 10% filled sample shows the best permeability of the gases, minimum permeability of the gases to the sample. So these are some of the references that are being used, and this work is done with IRMRA Bombay, and along with that, we two undergraduate students from our lab have worked on this. So I thank my team as well as all the audience for their patient hearing. Thank you so much.
Start my talk directly. Today I'll talk about tin oxide thin film grown on silver 111. It is a thickness and temperature dependent study. So why oxide surfaces? Because mainly, if I have a metal surface, most of the time the metal surface is always covered with some oxide because of the oxidation. So if I don't know the oxide surface, then I cannot know the behavior of the total material. And oxide surfaces are uses in catalysis, coatings, magnetic and non-magnetic data storage. But the main challenge in oxide is the preparation of epitaxial film so that we can study the band gap or band structure clearly. Now, as a sample, we have started tin oxide. Tin oxide has two main oxides of tin. There is tannic oxide and another is tannous oxide. Now, SNO2 is a tetragonal unit cell having rutile structure, and SNO is a layered structure having van der Waals gap between 2.52 angstrom. Now, the most interesting thing is that tin oxide can be used as a solid state gas sensor, oxidation catalyst, transport conductor. But this material is very less studied because it is non-availability of single crystal of SNO or SNO2, or it is very difficult to grow epitaxial film so that we can um, study the electronic property. And in addition to that, most importantly, as you can see this, generally when we grow a thin film, we differentiate it with XPS because it has different oxidation state. The SN has two oxidation state, SN2 plus and 4 plus. So they should show me two different binding energy, but as you can see that blue and red are at the same point, though one is SNO and one is SNO2. So they are showing me at a same binding energy. So this is very, very difficult to differentiate between SNO and SNO2 by XPS. So we have grown SNO on Ag11 at room temperature as well as high temperature. Now we have written it SNOX because we don't know whether it is SNO or SNO2 or a mixture of that. So generally author prefer it to write SNOX. So we have grown that SNO by evaporating SN in oxygen atmosphere, and we assume that one monolayer of SN gives to SNO, and we do the XPS after growing of each monolayer, and we can see that with increase in thickness, the SN3D peak shift towards the higher binding energy, and but oxygen is staying at the same. Only thing is there is some hump at the higher binding energy that we can see. So if I do the fitting by CASA XPS software, we get two component for SN, as we can see in the graph. To mainly two component, but there is a very little green component also there. But two component is mainly from one from SN4 plus, another is from SN2 plus. Now, whether we have grown SNO or not, that is the most understandable study is the valence band study, because XPS is not conclusive. So we go to a valence band study and we can see at around 2.9 EV at 10, beyond 3 monolayer actually, there is a hump is growing, and this hump is due to the SN5S derived level, which we can see in only SNO, not in SNO2. So this proves that there is a presence of SNO alongside SNO2. And when you do the low emission electron diffraction to know the surface structure, for this is the clean silver, we can see 6 clear spot. For one monolayer also we can see the silver spot mainly, but beyond one monolayer, 3 and 5 monolayer, we don't see anything. That means there is no ordered surface structure we can see. It is mainly a disordered structure. So basically at room temperature, there is no ordered tin oxide we can grow, and as a result we cannot study the electronic structure clearly. So we go to high temperature, we grow at 573 Kelvin, that is 300 degrees Celsius, and we have done the same XPS pattern, but now we can see clearly in the normal XPS also that SN3D has got a two different peaks. And same for oxygen, we can see the peak is shifted. So we do a careful fitting with CASA, and we see now we can see very distinctively 3 component of SN, mainly SN metal 3D0, then SN 3D2 plus and SN3D 4 plus. So 3 oxidation state is confirmed. That means not only metallic SN is present, but also 2 oxides are also present when we grow at higher temperature. The metallic SN actually present as an alloy with silver. And we have done the atomic contribution also, and we can see from the calculation that it is mainly SNO2, and with a few percentage with the grow, when you go to higher thickness, it is mainly SNO2, and SNO is very less, with a metallic contribution is very, very less. Okay. Now, if we go to the oxygen fitting also, at lower thickness, we can see 2 oxygen component, one from SNO and another from SNO2. But when you go to the highest coverage, that is 10 monolayer, we can see only one, and it is mainly due to the SNO2, because SNO is buried under the SNO2, and XPS cannot go that up to that thickness. And when you do the lead for highest order, we can see a very complex lead structure. This shows that there is a ordered structure, but this is very complex. The blue encircled one is the C2x2 pattern. Then we have this black encircled one as the 1/3 3x1 type of pattern. Then we can see some multi-domain, which is this purple is showing some hexagonal multi-domain. So because of the presence of metallic SN, SNO, and SNO2, the lead pattern is more complex because of all these three present there. So in summary, what we can see is that we can say tin oxide grown at Ag11 at room temperature as well as high temperature. For room temperature, only one oxide phase was seen for low coverage, whereas both SNO and SNO2 are noticed for 10 monolayer coverage at higher one. No lead spot were noticed beyond 3 monolayer, confirming that no ordered oxide was grown at room temperature. For high temperature growth, the presence of metallic tin along with two oxide phase confirmed by XPS. Complex lead pattern was found where we see C2x2 and 3x1 pattern. We have also done band structure study, but I have not shown here because of the time constraint and also the number of slides and all. So we have done the band structure study also, but it is not a very easy one. It's very complex one because of this, all this present here. So that's what we have done. Thank you.
So good morning, everybody. Myself, Dr. Swaroop K. I'm working as assistant professor in Department of Physics, GM Institute of Technology, Davangere, Karnataka. Today's my topic is synthesis of hydrogel nanocomposites by radiation assistance for biomedical applications. So before coming to the topic, we shall introduce ourselves with hydrogels. What are hydrogels and what are the properties of hydrogels? Hydrogels are the three-dimensional hydrophilic polymers networks which do not dissolve but can swell in water. It means the name itself says it is a hydrogels, means it is having an ability to absorb water. Okay, that is the main property of this hydrogels. And when the hydrogels were swelled in some aqueous solutions, it will expand more. Means based on the expansions, we will characterize for the swelling properties and other things. Based on the swelling properties, we can assign the particular hydrogels for particular applications. So, and they also have the ability to absorb a large quantity of water and retain it even under pressure. So you can observe some diagrams over here. So if we bend it or crush it, whatever we do, so it will regain its original shape and size after the external mechanical force has been removed. So by the definition, the water must constitute at least 10% of the water. The hydrogels, at least the material should absorb 10% of its original weight of the material. So then they are called hydrogels. Okay, so they are water insoluble, means as I told you, they will absorb water, but the thing is the polymeric network do not dissolve in it. Okay, so do not dissolve in it, and hence these are water insoluble three-dimensional network of polymeric chains that are cross-linked by chemically, physically, or any other means any other in the sense radiation means. So polymers are capable of swelling substantially in aqueous conditions. Polymeric networks in which water is dispersed throughout the structure. So these are the some what you call images. You could recall we have observed these kind of water balls for growing money plants and other things in our home as well. Okay, so these are also hydrogels. Okay, you can look into this. So this is yeah, these are the dry hydrogels. When it is been swelled, it looks like this. So these are all means probably this is a PBA hydrogels, and so when it is been swelled, it is actually a transparent material. So it will look like this. Okay, so for explaining the swelling capabilities, so you could observe over here. So this is the dried hydrogels, and when it is been swollen in the aqueous solutions, it will expansion. The expansion of the cross-linking will happen, and it looks like this. So how it can be swollen? Otherwise, how stimuli responsive hydrogels will behave? Stimulation can be done with ions, voltage variations, with a pH, temperature, and many other means. Okay, so if these kind of parameters have been changed with a particular hydrogel, the swelling capabilities also may be tailored. And presently, it's an a generation of super absorbent hydrogels. What are super absorbent hydrogels? We cannot define that, but we can consider 95% of the water absorbance if the hydrogels is having. Then these kind of hydrogels can be considered as super absorbent hydrogels. Super absorbent with a stimuli responsive behaviors. Otherwise, stimuli responsive hydrogels will considered as a third generation hydrogels. So coming to the classification, the hydrogels, as I told you, they are nothing but the polymers. So only the capability. Otherwise, why it is been named in a different word means it is capable of absorbing more amount of water. So the cross-linking methods also varies over here for the regular polymers. So there are three kinds of cross-linking mechanisms. So one is physical cross-linking, chemical cross-linking, and radiation cross-linking. We will be in our next slides, we will be looking into the aspects of radiation cross-linking and its advantages. So in physical cross-linking, freeze-thawing, ionic interactions, complex coaxiation, H bonding, and other things are there. So in chemical cross-linking, we have to use the chemical cross-linkers, and means an external chemical agent has to be added to the during the cross-linking process. So in radiation cross-linking, we do not use any kind of thermal, what you call cross-linking methods, or otherwise chemicals will not be induced to the what you call the aqueous solutions. Aqueous solutions are in the sense precursor materials. So it can be formed in the form of, means the precursor materials can be in the form of aqueous state, paste state, and solid state. So by looking into the physical cross-linking techniques, freeze-thawing method is there, complex coagulation is there, ionic interactions are there. So otherwise in the chemical cross-linking technique, water soluble monomer will be there, and an addition of cross-linker, chemical cross-linker will be added, and the cross-linking process happens like this. Okay, so after the purification, the remaining residual cross-linkers, chemical cross-linkers, can be removed after the washing. Okay, so the purest form of hydrogels can be found. But the main problem with the chemical cross-linking techniques is somehow some residue of chemicals will still remain in the final product of the hydrogels. So these kind of materials are harmful, or otherwise we could call it as hazardous when it is been applicable for the biomedical applications, when it has been routed to the biomedical applications. So similar to the chemical cross-linking techniques, in radiation cross-linking technique, we do not use any kind of chemical cross-linkers. Instead, we use gamma, X-rays, and electron beam, heat, or cross-linking other agents. Okay, so here, these gamma or X-rays are any what you call irradiation process we undergo. So these irradiations will produce some byproducts in the form of free radicals. Okay, so these free radicals will be utilized for the cross-linking, and final hydrogel product will be formed. So here, the only advantage of radiation cross-linking over chemical cross-linking technique is there is no chemical residues will not be remained in the final product of the hydrogels, and they are very much suitable for the biomedical applications. So as I explained, so one of the other techniques which is been used in the biomedical field is sterilization of the products. So radiation sterilization is also one of the important topic to be covered. So here, during the irradiation, otherwise during the synthesis itself, we can sterilize the product. means there is no external sterilization methodology need not to be adopted. So during the synthesis only the sterilization will be happened. So and that one more thing why it has been advantageous is it is simple and compact technology. So and the as I told you, there will be no residual ballast materials, residues or toxic initiators, cross-linking agents, and any other things will not be there in the final product of the material. So and it is clean and safe for human beings as well. And coming to the hydrogel nanocomposites, what are hydrogel nanocomposites? By adding the name itself says, so the adding the nano materials to the hydrogel networks will make a nanocomposite, means hydrogel nanocomposite materials. Okay, so we can add some metallic metal oxides, clay, and carbon nanotubes into hydrogel matrix, and hydrogel nanocomposites can be found. Hydrogels have why it is important means we can improvise the mechanical strength, stimuli responsive behavior, biological interactions, and optical properties and ability to remote activations can be these properties can be enhanced. Okay. So how it is being done? So the hydrogel nanocomposites, the preparation, there are 4 preparation methods. First 2 are chemical cross-linking techniques. Here we are using, in the first technique, the polymer means the monomer or the polymer will be used, and the chemical cross-linker will be added, and the prepared means ready nanoparticles will be added, and the gelation process by means of this chemical cross-linking will be done, and the final product hydrogels will contain the nanoparticles which has been induced within the hydrogel networks. In the second method, a polymer with a chemical cross-linker and a precursor material for the preparation of nanoparticles will be used, and during the gelation the precursor material will not be reduced to the nano size, and after that by using any other chemical techniques or irradiation techniques we can reduce these precursor materials into nanoparticles, and the final product there will be some there will be the nanoparticles which has been what you call isolated within the structure of the hydrogel nanocomposites. Coming to the third part, so here the polymer, we will take the aqueous polymers and the nanoparticles, prepared nanoparticles, we will add it, and the gelation will be done, and the final product will be ready. Means this gelation technique is a radiation cross-linking techniques. So in the final thing, so polymer will be there, and a precursor materials for the reduction of reduction to the nanoparticles will be added, and the gelation as well as in situ conversion both can be done in the single step, and finally the hydrogel nanocomposites can be formed. So these are some of the examples. So here, silver, gold, zinc oxide, graphene, and other particles which are been induced with a polymer matrix of gelatin, polyurethane, PVA, chitosan, PVA, and silk fibrons, and other things have been mentioned over here. And the cross-linking methods also have been mentioned. And there are some particular applications of these kind of cross-linking methods. Using these kind of cross-linking methods, hydrogels prepared using these kind of cross-linking methods have been mentioned over here. Okay, I am not telling hydrogel nanocomposites is the only hydrogel nanocomposites preparation by the radiation cross-linking is the only solution. This is not the only solution, but if you can opt for the radiation cross-linking, this is better than the chemical and physical techniques. And in many kinds of what you call preparation of the hydrogels, we cannot use radiation cross-linking techniques sometimes. So some of the hydrogel applications of hydrogel nanocomposites for the biomedical applications have been quoted over here. It is used for the drug delivery, biosensors and diagnostics, medical implants, antimicrobial membranes, skin tissue repair, vascular grafts, scaffolds, and other things. Okay. And wound healing as well. So so this is the gamma chamber where what we have used for the gamma irradiation, means radiation assisted hydrogel nanocomposite synthesis. This is gamma chamber 5000 GC 5000, what we call. So radiation synthesis we have used.
Can you conclude, sir? Can you conclude?
Yes, sir. Yes, sir. Just a moment. So these are the hydrogels what we have prepared. So these are the zinc oxide nanoparticles. These are the zinc oxide nanoparticles induced hydrogels, and these are the pure hydrogels. And this is the XRD results, which shows there is a trace of ZNO in the PVA hydrogels. And these are the FESM images, and this is the FESM image of the pure zinc oxide, and this is the hydrogel nanocomposite, and it is the TEM image. And the swelling studies have also shown that there is a good number of good amount of gelation as well as equilibrium swelling water content, and other things have been noted over here. And mechanical studies also have been studied, and it is shown that the tensile strength and the Young's modulus have been moderately increased with a small decrease in the elongation percentage. Means that there is no much variations in the mechanical properties when it has been studied. So finally, so the zinc oxide nanoparticles what we have prepared by the radiation cross-linking techniques is one of the what you call safe to use for the biomedical applications, with the properties like a good crystallinity properties, which with a good what you call mechanical properties and swelling properties. So these kind of materials can be used for at least for the wound dressing applications and some of the biomedical applications. With this, I conclude my talk.
Good afternoon to one and all. I am Tamanna, currently pursuing Masters in Physics from Netaji Subhash University of Technology. Firstly, I am very grateful to the organizer for giving me an opportunity to present my work on the topic Morphological and Optical Analysis of Tungsten Oxide Nanosheets for Gas Sensing Applications. So here is a list of contents, which includes introduction, synthesis part,
Tamanna, your voice is breaking. Hello? Am I audible to you, Tamanna? No, your voice is still breaking.
Sir, I am audible now?
Yes, you are audible now.
Okay, sir. So here I start with the introduction part. The current work focuses on tungsten oxide, which is well-known transition metal oxide that demonstrates stability and non-toxicity in its nanoparticle form. Now, there is a question arise, why should we choose WO3? Firstly, WO3 is used in gas sensors, especially for detecting nitrogen dioxide gas, also called NOx gas. And secondly, its versatility in electrochromic devices such as smart screen and displays, where its transparency may alter in response to an applied voltage, catalysis, and energy storage also. Now, there is next part, there is a 3D model of orthorhombic WO3, where the blue atoms represented the oxygen and yellow atoms represented the tungsten. Now I am going to the synthesis process. Firstly, we took a beaker with 30 ml of DI water and added 0.096 molar Na2WO4 sodium tungstate into it. After that, we have put the beaker on the magnetic stirrer for stirring for up to about 30 minutes. And then we have moved to the next procedure, and 5 to 10 ml NHNO3 was added to the solution dropwise and also stirred for 30 minutes. After that, oxalic acid of 0.249 molar solution was also added dropwise, and which changes the color of the prepared solution, and we get the solution of WO3 as also shown on the figure above. After that, the precursor solution was transferred into the Teflon in the hydrothermal reactor. Finally, the prepared solution was later centrifuged and washed with DI water and ethanol several times. After that, the finally precipitates were collected and dried in a vacuum oven at 60 degrees Celsius, and then the sample was then grounded to obtain the WO3 particles. The powder was then calcinated and presence of oxygen for an hour at 500 degrees Celsius within a heating rate of 1 degree per minute. Finally, I'll move to the result and discussion. Firstly, X-ray diffraction. X-ray diffraction pattern for the synthesized powder sample was observed within a range of 10 degree to 80 degree for 2 theta degree position. And the Debye formula has been often used to determine the crystallized size, as we all know. And the crystallized size of WO3 tungsten oxide was approx 23 nanometer. After that, crystallized size and strain was obtained by using the Williamson-Hall plot, and the crystallized size obtained to be 46.04 nanometer using the equations, and the strain to be 0.00325 respectively. Finally, the crystallized size calculated by size strain plot is 19.85 nanometer and strain to be 0.00229 using the equation. Now, absorption spectra by the UV visible spectroscopy. UV visible spectroscopy was performed for as synthesized sample using the diffusion reflection spectroscopy in a wavelength range of 190 nanometer to 850 nanometer, and the maximum absorption peak for WO3 was observed at 3 to 8 nanometer as shown in the figure. The equation used for this is shown below. Now, we move to the top plot. Top plot here, the optical band gap of WO3 was obtained using this method, which is to be 2.56 electron volt as shown in the figure, and the refractive index was about to be 2.53, which used the equation given below. Now the morphological analysis, which is shown by this figure, there tend to be thin flat construction with a high aspect ratio resembling the paper sheets within the range of 100 nanometer as shown in the figure. FECM also include the EDS spectra, which reveals the elemental composition of the sample. And here, as shown in the figure, the highest peak of the tungsten and oxygen are present in the sample. Finally, I conclude my work. The current work emphasizes on the structural and optical study of WO3 for applications in gas sensors. And the XRD analysis revealed that the material's crystal structure has orthorhombic symmetry. After that, the SAM analysis of the synthesized sample revealed the formation of the 2D nanosheets. And the band gap obtained from the top plot is to be 2.56 electron volt, and using the Debye equation to be crystallized size is about the 23.15 nanometer. And then the crystallized size and strain was also calculated by using the WH and size strain plot, as already I have mentioned. Now the future prospects. WO3 is widely explored for photocatalytic properties and has been proved useful for the environmental cleanup, water splitting for the production of hydrogen. WO3 has also widely used for the electrochromic devices and the gas sensing applications. Thank you for your attention.
Good afternoon to everyone. Myself Tripti from Kalinga University. First of all, I want to thank the organizer for providing me the platform to share my ideas. The topic of the presentation is exploring the applicability of phosphors in the various fields. These are the contents of the presentation. So in this presentation, we are basically focused on the previous application of the phosphor material, that is on the display devices and for fabrication of LEDs. While along with this application that is for the fabrication of LED, the most recent application of phosphors are explored, such as in the smart agriculture, optical thermometry, and in the for the detection of fingerprint and the lip print recognition. So as we know that when the lighting technology come into existence, the phosphor converted LEDs give considerable attention due to their various advantages. That means such as the LED based lamps produce a very bright emission intensity as well as the long lifetime span, and they also contribute to save the earth's resources, and the material consumption is diminished. In this line, in 2014, the 3 Japanese scientists won the Nobel Prize for the invention of the novel blue light, because we know that the blue light enables to generate the energy saving white light emitting diodes. So in this for this invention, the 3 Japanese scientists won the Nobel Prize. So these LEDs can be fabricated by using the phosphor materials. What is the question is that what is phosphor? So actually, the phosphors are the materials that produce the exhibit the phenomena of luminescence. The basic building block of the phosphor materials are the host lab material or the host lattice activators and the co-activators. The co-activators are not always necessary, but sometimes if needed, the co-activators are also used. So these three building block can be detailed in detail in this slide. So the first building block is the host lattice. In general, there are two types of host lattice are used. That is the organic materials as a host lattice and the inorganic materials as a host lattice. But as compared to the organic materials, the inorganic materials are much more used as a host lattice because of their resistive nature towards the environment, because we know that the luminescence is the structural based study, and as the structural changes, the luminescence properties also get changed. So as compared to the organic material, we can prefer to use the inorganic material as a host lattice. For the formation of inorganic host lattice, the one or more cation can be combined with an anion or an anionic group, and based on this anionic group, the host lattice can be, there are several host lattices are available to be used as a phosphor material such as sulfides, borates, phosphates, vanadates, tungstates, and so on. The next building block is the of the host lattice is the activators or co-activators. The co-activators is also known as the sensitizer. So for choosing the co-activators or activators, it should always be kept in mind that the activator must be always optically active, because the overall absorption and the emission can be take place at this lattice site. There is a wide energy gap between the emitting and the ground states within the crystalline hole, so that the large energies, we can receive the large energy. The another important factor while choosing the activator is that there is a proper matching between the valence state and the size of the dopant ion and the substituted cation of the host lattice, so that the dopant get easily stabilized into the within the crystalline host. There are two possibilities for the choice of activators or the co-activators. The first one is the transition metal, and the second one is the rare earth element. But instead of transition metal, the rare earth element are mostly preferred, because the transition metal consists of the these d electrons, and we know that the d orbitals possess the very closely energy levels, so that there is a high chance of non-radiative transition as compared to the radiative transition, so that the luminescence properties get diminished. The other one is the killers or quenchers of luminescence. So as we have discussed in the choice of activators, sometimes in many dopants, when doped in an improper host lattice, instead of enhancing the luminescence properties, they act as a quenchers or killers of luminescence. That means they diminish the luminescence properties of that particular host lattice by creating an energy sink, so that the absorbed energy is released non-radiatively without releasing the energy in the visible region. So in order to prepare an efficient phosphor, there is some parameters that should always be kept in mind, so that the synthesized phosphor will be highly efficient. So these phosphor parameters are broadly categorized into the two categories. The first one is the independent variable, that is those variables which are totally independent from each other. These are the purity of material, that choice of host lattice, activators, and so on. The another parameter is the dependent variable, that is that depends on each other. For example, that is the firing temperature and the firing time. Yeah, so the firing temperature and firing time is depends on each other. If the time is greater, that material will be not properly synthesized. If the temperature is greater, the material will be not properly synthesized. That means particular time and temperature is needed. So such parameters are known as the dependent parameter, because they depend on each other. So these parameters should always be kept in mind while preparing the phosphors. Now, based on the application point of view, there are various type of characterization techniques are used. In this talk, we are basically focused on the application of display devices as well as smart agriculture and fingerprint detection. So here we have to discuss about the spectroscopic techniques that generally measures the wavelength or the energy Photoluminescence. Photoluminescence comes under the spectroscopic technique of optical characterization. It is a type of energy conversion type luminescence in which the specimen under investigation is get excited to the ultraviolet or the photons of ultraviolet or the infrared region as an external source of energy, and subsequently produce the absorbed energy in the form of visible region. This type of phenomena is known as the photoluminescence, because here photons are used to excite the material. So this overall phenomena can be picturized in this configuration coordinate model. Here we can see that after receiving the energy, the electron gets excited to the higher energy levels, and following the Frank codon principle, from here the excited electron gets relaxed to the lower vibrational level, and from here it may transition accompanied by the emission of radiation in the visible region. This difference between the excitation and emission spectra is denoted by del R, and it is known as the Stokes shift. The spectral response of this process can be picturized in this picture, and this difference between the excitation spectra and the emission spectra is known as the Stokes shift. From here, with the help of this spectra, by knowing the wavelength or by knowing the energy, we are able to know about the emission color of the phosphors. But this is generally, we can realize the emission color. In order to represent this color emitted by the phosphor materials, with the help of coordinates. So CIA coordinate diagram is used. In this coordinate, we can see that the various regions are divided on the basis of different colors. So by plotting the emitted graph in this plot, we came to know the perfect color of the phosphor material that is emitted by the phosphor. So on the basis of this color, we are able to fabricate the light of that particular color. That means if we use the European iron doped material, that means it emit light in the red region. So by using this phosphor material, we are able to fabricate the light of the red color, or sometime when get excited, we are able to fabricate the light of the white color. So there are several works are going on for the fabrication of the white light by doing many modification in the host lattice, or by using different host lattice. That is, for example, in the first literature, the author replaced the magnesium and silicon in place of the aluminum in the commercial yak phosphor, and his findings reveals that the CCT of the phosphor is too low, that means up to 4000 Kelvin, while the CCT of the correlated color temperature of the commercial phosphor is greater than is up to 8000. So the CCT is low by modification of the host lattice, as well as by using the different lattice, we are able to increase the efficiency of the LED that is fabricated. That here in the next literature, this author reports the non-rare earth doped red emitting phosphor material. This material able to replace the commercial oxynitride phosphorus. These are the papers of mine. Our group was also continuously work in the generation of single phase white light emitting diodes. Here in this article, we are using cerium and dysprosium co-dopant in single strontium aluminum silicate based phosphor. In this paper, we are trying to develop a lithium strontium silicate based phosphor doped with europium for the production of white light. In this paper also, we are trying to develop a red phosphor by using the different host lattice. So instead of the application of phosphor in the fabrication of LED, the recent application of phosphor in the smart agriculture. So now the question is needed, why we need a smart agriculture? As we know that in India, most of the economy of the country are agriculture dependent. Okay. But for the proper growth of plants, for proper growth of crops, the most important criteria is the ambient atmosphere, proper light and water. But in the rainy season, and this light can be received from the sun. But in the rainy season, or in the cloudy season, the plants didn't receive the proper light from the sun due to the cloudy reason. And in that case, there is a failure of crops, which causes the various loss to the farmers. So in order to increase the cultivation in the unambient atmosphere or in the rainy season, also or under unfavorable climatic condition, there is a need of indoor farming. So in the most essential criteria is to develop a light source that is whose spectral response matched with the photosynthetic spectra of the plants or the sunlight, so that the plant can grow properly inside the room also. uh, by proper studying, we can find that only the two range of light source can help for the proper growth of the plant. That is the 400 to 500 nanometer light that helps to grow the plant in the direction of the light source. This process is known as phototropic process, and the 730 to 735 nanometer light is generally, it lies in the far infrared region, and it is used to the other photosynthetic process of the growing of plants. So our aim is to develop a phosphor that contains the dual emitting center, and that are able to produce or emit the light at these two particular regions, so that by using a single phase light we are able to achieve the both the emission, and that should be helpful for the proper growth of plant in the indoor farming. So this is one of the most important application of the phosphor material. On the basis of this, this article reports the sodium lanthanum phosphate material. It is a diphasic material, and due to the multi-site occupancy of the dopant ion and the coexistence of the EU2 plus and the EU3 plus ion, this material acts as a dual emitting material. That means it produces the red as well as the blue region light also. So this material is the most suitable for to fabricate the LED that is useful for the plant growth inside the room or in the indoor farming also. So these are the some basic needs of the indoor farming. Now, next important application is the optical thermometry. As we know that temperature is the most important fundamental physical quantities, and it is widely used in the various field of our daily life. So the most commonly used thermometer is the liquid gas thermometer, but the major issue that is always faced with the traditional liquid gas thermometer is that its uses is restricted in some areas, that is, or in some situation, that is in the micro and the nano size objects. This thermometer is not applicable. Fast moving objects, the thermometer is not applicable. In corrosive or environment or biological tissues or various harsh or hazardous conditions, this thermometer is not applicable. So in order to overcome these issues, the concept of non-contact optical thermometer came into existence. So for the optical thermometer, the inorganic compounds such as borates, vanadates, phosphates, fluorides do considerable attention, as they this type of inorganic material show high resistance to the high temperature and photobleaching treatment. But the optical thermometer, to prepare an optical thermometer, can be realized by using the temperature dependent optical parameters such as fluorescent intensity ratio, lifetime intensity, and so on. Of these techniques, the fluorescence intensity ratio technique contribute to the obtaining the high measurement. It is very reliable and the high accuracy technique. So this can be obtained, the fluorescence intensity ratio can be obtained by between the two thermally coupled energy levels with the help of this formula. And based on this fluorescence intensity ratio, the absolute sensitivity and the relative sensitivity of the phosphor materials can also be determined. And by using this, we came to know whether the phosphor is able to be applicable for the thermometer or not, for the optical thermometer or not. And these are the literature that works in the field. So here in this spectrum, we can see that here the dopant, that means the calcium, magnesium, phosphate, the dopant U2 plus site can be show the multi-site occupancy. That means they are able to occupy at the calcium site as well as the magnesium site. So due to the multi-site occupancy of the dopant in this phosphor material, they are able to produce the dual emission. That means when they occupy at the calcium site, they produce the blue emission, but when they occupied at the magnesium side, they are able to produce the red emission. So with the help of this, we can easily, fluorescent intensity ratio can be easily find, and subsequently find the absolute sensitivity of the material as well as the relative sensitivity of the material. And so this type of multifunctional or bifunctional material can be easily useful for the plant growth as well as the optical thermometers. Now next and the last important use of a phosphor material is in the detection of fingerprint. We know that in forensic science, to find a culprit person, fingerprint act as a most essential evidence, because we know that the fingerprint of any person cannot be changed and it may vary from person to person. It is the characteristic of a particular person. So, but sometimes the fingerprints are not detectable by the naked eyes. So, in order to detect the fingerprint, this type of fingerprint, which is not detectable by the naked eyes, is known as the latent fingerprint. So this type of fingerprint can be, to detect this type of fingerprint, several techniques are used, such as the mean hydrogen test as well as the powder dusting test. So of these techniques and many more of these techniques, the powder dusting techniques is the most efficient techniques, and it is easy also. So we generally use, the forensic expert generally use the powder dusting techniques. The powder that is used for this technique is a luminous powder. So in place of that powder, we are using our phosphor material or the nano powders that we prepared with the help of, generally the phosphor materials used for the powder dusting techniques can be prepared by the soil gel method or the auto combustion method. So just where the fingerprint is observed, the powder is spread over the fingerprint and the extra powder can be blown off. Now, so that the powder, nano powders can be stick at the sweat pores of the fingerprint that is available on that surface. Now that surface is exposed under the UV radiation, so the phosphor material can glow, and with the help of this, we can easily detect the fingerprint, latent fingerprint of that person, and found the culprit person. So in this way, in conclusion, we can came to the conclusion that along with the display devices, some other applications are also available with the phosphor materials, and which are recently used, and they are very advantageous applications. Along with the fingerprint, lip print can also be detected in the same way by powder dusting methods. The other applications are the anti-counterfeiting or some other methods. Thank you for your kind attention. Any questions?